So I'm with the University of Rhode Island. Who knows where Rhode Island is? It's a tiny state. It's actually the smallest state in the United States. It's like Goa. It's the smallest state. It's near Boston, New York, right between. The University of Rhode Island is a research institution with about 16,000 students, undergraduate, graduate. We have PhD programs. I'm in the Department of Geosciences and also jointly appointed to the Department of Civil and Environmental Engineering. Like my colleagues, we share interest in water, and the university is building a water center, which, like TERI University, is very multidisciplinary, and we are hiring new faculty. We already hired 3 faculty. I just found out that 2 more will be hired. So we're building strength and we're building competence, and from what I've seen, you guys learning the types of classes offered are very similar to what we building at University of Rhode Island. And this is, again, very timely because water is the issue of this century. People talk about oil and how we're running out of oil, and everybody's worried about that. Okay, you cannot drink oil, but you need water, right? So water is really the issue, and possibly many conflicts in the future or already now are about water. So if we think and learn and study these issues, then hopefully we can contribute to resolving or addressing these problems, which will be with you for the rest of your life. I will be long retired, but it is up to you to make the decision in the futures. So it is important that you have the best knowledge you can get, and that's why you are here. I will give you a lecture now about my experience with River Bank Filtration. I studied River Bank Filtration in 2 actually some other areas, but I will only talk about Jordan in North Africa, Arabia, and in India. So I will briefly introduce you to what riverbank filtration is and why we need it, and then I will show you some data from these test sites, show you what riverbank can do and what it cannot do. It's not a holy grail or a silver bullet. It is just one technology of many. Okay? Let me start with a statement by the former USAID Administrator, Dr. Sharif Shah, who basically states what I already said, that water is at the center of our many of our problems, and improvement in water productivity can help change the life of millions. That's just stating the obvious, but the problem is, how do we get there, right? I mean, this is the vision. So let me start with what I would expect from safe drinking water. Safe drinking water to me means it has to be free of pathogens, no E. coli, bacteria, viruses, protozoa. That's not anything, nobody wants cholera in their water. It should also be free of particulates. Particulates meaning the water should be clear. Particulates, their presence indicate pollution, visible pollution. And it also should be free of those inorganic and organic compounds, heavy metals, industrial solvents, and whatever else can be in the water, because this is usually the invisible pollution that makes you sick, long-term sick, cancer, neurological diseases. The pathogens cause you diarrhea and gastrointestinal problems. This stuff kills you long-term. So none of that material should be in safe drinking water. And of course, how to get these pollution in the water? There are many sources. I can spend probably an entire day talking about it. Everything from agricultural to sanitation, hygiene, patterns. Stormwater can be a conduit of pollution. Lots of pollutants enter the environment via stormwater. Leaking underground storage tank, petroleum, gas stations, right? The disposal of medications or other medicine that goes through your body back into the environment. It's an emerging field of concern, as these compounds are very bioactive, estrogen disruptors and whatnot. So there are lots of sources of pollution, the question is, how can we treat them? And there are technologies, and I've heard there are some people here that deal with wastewater. These are very sophisticated, high-cost infrastructure projects which do a good job, but they are very complex, needs experts, and typically they're not in reach for financial reasons and for operating reasons. So small communities in rural areas can't afford it, is completely out of question. Remediation, meaning cleaning up these polluted sources in the ground, on the surface, also possible, but again, it's technologically complex and costly, very costly. Same argument, it is not applicable to rural areas in most developing countries. Stormwater treatment, this is being discussed in the United States right now. Many towns have to implement what is called best management practices, stormwater treatment systems like this tree filter or this what's called a vortex system or a separator unit. They're being built into the drainage system to capture pollutants before they reach rivers or the ocean or lakes. Area of great research. We do this a lot at the University of Rhode Island. We have an entire field site dedicated to testing these stormwater treatment technologies, and I'm very excited about it because it's great work for students. So again, it's nice, but it's costly. So what we need are, first we have to realize that many of these structural best management practices, or BMPs, are too costly or too technological complex to be implemented in most developing communities. And I'm thinking about more the rural areas right now, but also the urban areas here in New Delhi, for example. So what I propose is that we need to think about unconventional systems that are sustainable and low cost, right? That can be developed and field demonstrated. But that has to go hand in hand with community outreach activities that change behavior. Behavior change and attitude change towards water and the environment have to go together with these technological solutions. Only then can we succeed. Technology by itself doesn't do it. It needs to be a holistic approach, right? So what I'm proposing as a simple unconventional technology is river bank filtration. And it's a really simple technology. Some people will say, oh, it's not a technology at all. We're already doing this. Well, yeah, maybe you're doing it, but the trick is the engineering part. In this case, let me briefly explain. So we have a river, okay, and we have groundwater. The two are connected. The river is mostly polluted. Go down there to the Jamuna River, very polluted, right? Now, if we can filter this water and bring it to at least the degree where it can be used safely for irrigation or possibly domestic use, then we can make use of this water resource, which otherwise is get wasted because nobody can or should not use it. So the idea is to install a well near the river and start pumping water and induce the flow of water from the surface through the alluvial aquifer towards the well and then pump it to the surface. There are many issues here. There's an active layer right here at the interface between the river and the alluvium, which is called a biofilm or culmination layer. Biologically very active, is very effective in removing pathogens and organic materials. And then we have this long distance, which is basically a gigantic sand filter, right? And sand filtration is very effective, and we can have a sand filter 100 meters long. That's just one distance. We typically plan drilling these wells 50 meters to 100 meters away. It depends on the local geology, how far the setback distance is. And this is where the engineering comes in, because you have to determine, either by using models or hydraulic tests, what is the residence time of the groundwater from here to here. We're aiming for about 2 weeks. 2 weeks have proven to be effective in removing bacteria by 2 or 3 orders of magnitude. So 99.9 to 99.99% removal. So the engineering part is to determine the appropriate setback distance, because if you're too far, you don't get the surface water. If you're too close, you don't get the degree of treatment. And that's where the technology comes in, right? These processes that I'm describing here that treat the water are all natural. There are no chemicals involved. So we're relying on sorption and predation of bacteria. We're relying on ion exchange, degradation. These are all in situ processes, and the beauty is they're renewable, because the river is a dynamic system. Every monsoon, for example, the layer that has the contaminants gets scoured by the floods, and it takes about 2 weeks to rejuvenate, and then the system is back to full capacity. And there are systems in Germany that are in operation for 120 years. Same idea, 120 years. This would be the Rhine River. It was one of Europe's most polluted rivers, and still they have been using the system for about 120 years effectively. And to make my point, the German capital of Berlin, right here, 75% of their water comes from a system like this one. The Netherlands, they get about 7% of their national water from systems along the Rhine River mostly. The potential in the United States is estimated to be about 70 million people, but not too many systems actually exist in the United States. The full potential there has not been exploited. So the question is, how many of these systems can be possibly built in India? And that's where my research comes in, because India is different in many ways. You have a monsoon climate, a prolonged dry season, then the degree of pollution is much higher than what you will find in Europe or in the United States. And there's also some cultural issues to make the system work in a different societal context, where most people have not been paying for water or do not know the value of safe water and being charged for it. So this is the kind of research I'm interested in. I show you two examples from, I'm going to jump over this. This will be information you will have available. I just want to have more time for questions later. So the two examples I am talking about is one in Jordan and one in Karnataka near the Kali River. Okay, so the first one is Jordan. Anybody been to Jordan? Oh, here we go. Amman, the capital, right? It's, where is it? Somewhere here. And Jordan is a very, very dry country. Very dry. There's very little water. There's basically the Jordan River coming in here. That's the border to Israel. Here's the Dead Sea. That's all salt water, completely useless. There are few small rivers, the Jamuk, the Sakar, some oases, but dry. Mostly this is desert. Here's Saudi Arabia, Iraq, Egypt, very dry place, very little precipitation. And a lot of people living there, and more so with the refugees from Syria. Water is a big problem in Jordan. So the question was, the little surface water they have, which is also heavily polluted, can we use it possibly before it disappears and becomes useless to the community? So we focused on one river, the Sakar River, and this is it is a river, but it's not really, because its source is the sewage treatment plant of Amman, the capital. So during the summer, most of its water is basically the effluent from the sewage water treatment plant. And that's how it looks like. And it is really optical, visibly contaminated. It has everything you don't want in the water, including high loads of turbidity, bacteria, and whatnot. Yet still people pump it right out of the river and use it for irrigation. It's prohibited by law, but it's done anyway. The problem is the crops they're growing, nobody wants to buy because they're so heavily polluted. The lettuce, for example, the greens are all coated in toxic stuff. Nobody wants to buy it, and that's a problem. So we focused on this river And oh yeah, so here's basically its source. That's, so to speak, the source of the river. And then as it moves through Iran, northern Jordan, it is not a very long river at all, but you get the idea. Little bit of water quality parameters. You can see the total dissolved solids, very high, BOD, COD, chemical oxygen demand. Then the other parameters like bacteria. See that? These are huge numbers. You don't want any of these bacteria in there, yet you have much higher numbers. Yes? Oh, sorry. I have a
question, but I don't know if I should ask now. Maybe you come to that.
Maybe we wait. Okay. I'm hoping we have enough time afterwards to answer questions. So the field site was established about halfway along the river before it leaves Jordan. And it was installed on a meander bend. So the river comes around here. It's not a big river. It comes around here and then goes over there. We installed several wells. We only need one, but for research purposes, we drilled many more, about 5. And here's a picture of such a well. The well was equipped with a motor, with a pump, and we conducted tracer tests. We conducted water quality sampling, and we compared the effluent, the water in the river, with the water pumped from the well. That was basically our way to compare how effective the system is. And here are some of the results, only focusing on bacteria and pathogens in general. Removal in log units, more than 4 log units removal of bacteria, E. coli. Enterococci, 3.2 log units, phages, and other viruses, basically around 3 orders of magnitude. We were very happy with this outcome. It means basically the risk from that water that we calculate, the risk reduction is about 2,000 to 2,500 times lower risk. And this water is being used now for agricultural purposes, for a landscape business that is using that water to grow plants, and they're very happy with it because it's their own treatment system, and it costs them basically nothing except the electricity for running the pump and the occasional cost for water analysis to ensure that the system is still running. This study was funded by NATO. They have a special program for Mideastern countries. It was in collaboration with the Jordan University of Science and Technology and the Water Authority of Jordan. Now moving on to the second example, and this one is from India. It is slightly different because in the first Jordan example, we were only concerned about the engineering, only about how much can we remove, how far does the well have to be set back from the river, and geology, hydrology. The second India example also had the community element. So not just quality of water, but also can this system be translated into a community-owned and operated water treatment system? And what is its acceptance? How can it be sustained over the long term after we have left? So this is really the core here, more than just science, but community building. The study site is along the Kali River, which is west flowing. So one of the few rivers that's west flowing. It's about 160 kilometers long. Enters the Arabian Ocean right at the border of Goa and Karnataka down here. This is just a picture of the river. I show you more. I don't know if it's visible. Can you see this slight contrast in color? There's a huge paper mill here. It's India's largest paper mill is just about here. And that's the effluent from the paper mill mixing with the water of the river. And I say this is treated water, but there's a bridge over here, and if you go there, you need a gas mask. It's that bad. I mean, there are bubbles coming out of the water, and it is quite polluted. So the project was implemented in 3 stages. The first stage was a reconnaissance study, finding appropriate sites having the right geology, hydrology, having the right community that we wanted to work with. The second phase was the installation and testing of the river bank filtration system. And then the third stage was community education and building a business around river bank filtration. So I'm going over these phases one after another. There were many existing sources of water in the area. Some of them ancient wells, dug wells, open wells. This was actually the main source of the community we were working with eventually. As you can see, the water is optically, visibly polluted. There's some bore wells. This one, like many, had failed, didn't work anymore. Other NGOs, other schemes implemented water tanks. Some of them were working, but we tested them all for E. coli, bacteria, and all of them were heavily contaminated. And probably lack of maintenance is one of the major issues. Water towers, sure. This one wasn't operating for the last 3 years because the pipeline bringing in the water was broken. Nobody fixed it. So infrastructure is there, but the system is not being maintained because it is not community owned. Nobody takes care of it if it's not the responsibility of the community. Somebody else put it there, and after they left, it was done. We spent a lot of time testing, field testing the water. We involved students from a local college. One of my master's students at the time, she's now graduated, Pamela. We used some low-tech technologies like test strips to test for free chlorine, as you would suspect in effluent from a paper mill. We used GPS, we used pH, DO, electric conductivity meters, and we also sent samples out to professional labs to test for compounds that you need to have a GCMS for, or other metals, atomic absorption spectroscopy. So these are just some of the parameters we tested. All that information was implemented into basically Google Earth database. So all these registered GPS locations were connected to information. So if you click here, you get first a picture of the sampling point, its GIS coordinates, and then the parameters that were tested and analyzed for at this location. So, and then each of these were sampling points that we all put together. And the beauty is using Google Earth, it's free, right? So if you think about sustainable projects, if you have ArcGIS, that's much more powerful, sure, but nobody can afford it, at least not the colleges or schools in these rural areas. They cannot afford it, but they can afford Google Earth because it's for free. So it is out there. If you find it, you just click on it and then the information comes up. Oops, yep. Did I jump a picture? No. Oh yeah, okay. That's important. We also conducted a community survey before and after we implemented the system, the RBF system. We wanted to know what is the community thinking about water before we started. What is the health situation in those villages? How many times do people get sick? When do they get sick to their stomach? So we developed a questionnaire in Kannada. And again, we had hired a group of 20, 30 local students that went from house to house asking the household head about how they're doing, and we gathered all that information, and then we did it again afterwards. Okay, so phase 2 was actually installing the system. We brought in a drill rig. The drill rig drilled us 4 wells in one day. I was very surprised because from my previous experience in Jordan, it took us several months to get 6 wells installed. It was horrible. Here, one day, boom, done. We bought on the local market an Indian-made groundwater pump, very affordable compared to the European like Grundfos models. It's like 10 times more. So we bought it. We put in a water distribution system to the village. These tanks were installed. We started monitoring periodically for a 1-year period, measuring water quality at all these 4 wells that we drilled. And the next slide shows you where these wells are. So this is the Kali River flowing this direction. This is the land on which we installed the well. There was a road here, and we installed 4 wells, again for scientific reasons, each one a little bit farther away, from 29 meters to 79 meters. One thing you have to always consider with Indian rivers is that they have a huge amplitude of change. In the dry season, it can be very low, but in the flooding season, the river can be way higher and therefore spreading out. So one part of the reconnaissance is to find out where can I simply drill a well without getting inundated during monsoon. So in this case, we were very lucky. The riverbed came up, but not as high as to our wells. So all these wells were dry. These wells were about 25 to 30 meters deep. That was about the thickness of the alluvial cover in this area. And this is what the water looked like from the well compared to the river. River water, well water. You see the difference, right? Optically, visually, much better quality. What you don't know, of course, is there still bacteria in there. Even clean water can be polluted. I can tell you that water was clean. I drank it. I did only drink it after, of course, we had the analysis done. But after it was clear that the water was safe, it was very important actually to show that we drink the water too. It's not like, okay, you drink it and I don't want to deal with it. So here's some data. This is the initial phase when we installed the well. Initially, very high concentrations. As we started pumping and the system became active and these natural filtration processes began working, the contaminant E. coli concentration dropped to basically detection limit. We kept 1 because we don't know what the detection limit is. It's basically detection limit right here. Focus on the black squares, because that's our main production well. The other wells were research wells, as I explained. Some of them had higher measurements of E. coli, some of them had lower, but we decided to go with what is MW3. And this is the dry season, pretty much. Here's where the monsoon hits. Here's where the monsoon is over, and then dry season again. And you can see we had basically non-detects during the dry season. Monsoon comes, then we get some higher 10 counts, maybe a little bit higher than that in this case. And then as the monsoon is over, back to 0. Now, this seems high, but the river water, that is the alternative, was 3 orders of magnitude higher. So you can see that even during the monsoon season, where we have some hits, the water quality is significantly improved to what would be the river, which would be way over there. This is, of course, not perfect. The World Health Organization asked for 0 E. coli in the water, right? Now, we can do that during most of the dry season, but we have had little problems during the wet season. Is that necessarily a reason to shut down the well and say, okay, you don't get this water because it doesn't meet WHO standards? We said, no, we're going to continue delivering the water because it's 100 times, 1,000 times better than the alternative. So it's an improvement. It's not perfect during the monsoon season, but it's definitely better than the alternative. And plus, there's another reason. Later, we found that much of this E. coli is probably directly related to animals, cows, which happened to be on this farm near the well. And we didn't realize that. We later noticed that simply banning the cows as far away from the well as possible will improve the water quality. And unfortunately, I don't have the data to show it because the project was over. But when we remove the cows, people get even less sick from the water than before. So some of the results, the yield is about 8 cubic meters per hour. That was mostly because of the limitation of the pump. But it's enough water for 4,000 people, 55 liters per day per capita, which is the requirement, at least in Karnataka, I believe in all over India. That's the minimum amount of domestic water to be produced. The water is clear and free of odors, and the E. coli reduction is 2 to 3 orders of magnitude, as I have said. So the last phase was to transition this technology into local ownership. So we work closely with the community leaders, the college, local college, the paper mill we also worked with because they are very much responsible for some of the pollution and they were very willing to work with us. The village elders, this by the way is Dr. Chaudhry, formerly TERI, now working in Oman. This is Ms. Kavita Patil in TERI Goa, and she is explaining to the local villagers what is actually the system, how does it work? Because you can imagine few of these people have higher degrees. So explaining to them what is E. coli or what is hydrology or river bank filtration, it's very difficult, very difficult. It's much more difficult than what I can tell you because you already have a background. Many of them cannot read and write. So how we transfer our knowledge into the local knowledge is very important. And Mrs. Patil is very skilled and helped us a lot in doing so. So we had basically this phase, the community education phase, which basically was a very strong part of our project. And we also, like I mentioned, we conducted a post-study survey. We compared that to the pre-study survey. These are self-reported numbers, so you always have to take it with a grain of salt, meaning people, when asked, give you the answer you want, right? You heard about that. So we were trying to ask questions that minimize this risk, particularly when it came to the health effects. We wanted to know as realistic as possible what was the impact. Before we started our system, about 21% reported chronic gastrointestinal disease. Afterwards, that number went down to 0. Is it really 0? The main point is it went down. It went down. I don't want to claim it was 0, but the water quality improved. And people were accepting the water. They didn't reject it for taste or for other reasons, as it often is the case if you use chlorination, people don't like that. Or if you use a bore well versus river water well, people have problems with that too. The other question we ask, are you willing to pay for this water? We set the price of water, I believe it was 50 rupees per household per month, which is not a whole lot if you consider how much you pay for just a bottle of water, right? About 2/3 said, yes, we are willing to pay. 1/3 didn't want to pay anything. And that didn't surprise me at all because, first of all, this was a very poor area. And second, traditionally, people in these areas never paid for water. But I think the education helped to make them understand that there is a value in water, meaning, yes, if I buy water, I get a product that keeps me healthy, productive, and allows me to continue working. And that's the connection the villagers made, and those were the ones that says, yes, we're going to pay. So here's the final handover. As you can see, the technology doesn't look like a whole lot, right? Later we buried this pipe, so there was a pipeline, so just for the handover we made sure everybody saw the water flowing, and like I said, we drank the water ourselves. And the water, the RFB was transitioned into a local water committee. 5 people in charge: the landowner, then the village nurse, the village teacher, the representative from the college, and the representative from the paper mill. So we wanted to have 5 independent people, so when money is involved and money is collected, that the villagers have several people to talk to, not just one person, but a water collective. And including the village nurse and the village teacher was very important because everybody knows them and there's trust. We made it very transparent. We put in a bank account. We trained them in basic business practices like keeping account ledgers, who paid, who not. So very transparent, so there was no distrust in the population. And that seemed to have worked. Ms. Patil was there 3 years, last year, after we stopped the project. We went away, it's still working. And people are still happy with it, and people still don't get sick. It seems that the transition into local ownership has worked. So we're very happy about that. So we succeeded in attitude change. We made people accepted that paying for water is a good thing. We also changed behavior. As I mentioned, the farmer realized that having the animals running around the wellhead is a bad idea, so he moved them away. Instead, he's now planting banana trees in this area, which is very good. And that lowered the bacteria concentration. This was a project in collaboration with my university, with TERI, and funding came from the World Bank, developing marketplace program. Oops. Yep, no, that's good. Conclusions. I think the take-home message is, to repeat myself, it is engineering plus community work. The two have to go together. So technology alternatives that are sustainable and can be operated at the local level because of low technical complexity are needed, but they need to be combined with community outreach that changes behavior and attitude. And most of you already know this, right? But it is important to not separate the two, but keep them together. And that was probably the main lesson that I learned from this project, and I was ever since intrigued by this type of project, and I hope future project as the one we're just starting in Karnataka, that's a new project funded by the Australian government. We're drilling 6 new river bank filtration wells and working with Monash University in Australia and their public health specialist. We're trying to create statistical data, biomedical data to prove that our system indeed changes the health of the people that get that water. So this is the new project that we're just starting. So more in 3 years. So, but now thank you for your patience, and I'm sure you have questions. And so please ask away. I'm happy to answer them if I can. Thank you.